Welcome to the Shikasa Boo Motor channel. This channel provides easy-to-understand explanations of car mechanisms. BYD employs a series parallel hybrid system in their plug-in hybrid Sealion 6, which is referred to as DMI. There are three major types of hybrid systems currently used around the world: power split hybrid, series hybrid, and parallel hybrid. Power split hybrids consist of two electric motors and a power split device, and they provide three driving modes: electric motor only, engine only, and combined engine and motor operation. Toyota, Ford, and Subaru employ this system. In recent years, this system has sometimes been referred to as a series parallel hybrid, but to avoid confusion, this video will refer to it as a power split hybrid. Series hybrids use the engine solely to drive a generator, while the vehicle is propelled by a traction motor. The engine does not contribute to propelling the vehicle. It is called a series hybrid because the power flow runs linearly from the engine to the generator, then through the traction inverter, and finally to the traction motor. Nissan and others employ this system in self-charging hybrid vehicles that are not plug-in. Parallel hybrids are systems in which an electric motor is added to a traditional powertrain that combines an engine and a transmission. It is called a parallel hybrid because there are separate power flows from the engine and from the electric motor. It is adopted by automakers such as Mercedes, BMW, Audi, Stellantis, Volvo, and Ford. This channel offers videos that explain the details of each hybrid system. Please check them out if you're interested. BYD system combines series hybrid and parallel hybrid architectures, and is therefore called a series parallel hybrid. The engine output shaft is connected to the generator through a speed-increasing gear. The engine is a 1.5-liter naturally aspirated unit, producing a maximum output of 72 kilowatts and a maximum torque of 122 Newton meters. What's remarkable is its thermal efficiency. BYD claims it reaches 46%. Let's see how impressive 46% really is by comparing it with engines from other automakers. Chery's 1.5-liter turbo engine achieves 44.5%, Nissan's 1.5-liter turbo engine reaches 42%, while Toyota's 2.5-liter naturally aspirated engine and Honda's 2.0-liter naturally aspirated engine both achieve 41%. For reference, let's also take a look at the efficiency of thermal power generation. Conventional coal-fired power plants have an efficiency of around 34 to 38%, while the latest supercritical and ultra-supercritical boilers achieve 42 to 45%. Combined cycle natural gas power generation is said to achieve around 60% efficiency. Logically, BYD's engine with a thermal efficiency of 46% would produce less CO2 emissions than a battery EV powered by electricity generated from a modern coal-fired power plant. However, it's important to note that even though it's an engine dedicated to power generation, it cannot always operate at its most efficient speed since it's still an automotive engine. Let's get back to the system configuration. The engine output shaft is connected to the engine output gear via a clutch. The engine output shaft is connected to the output shaft via a gear. The output shaft is connected to the traction motor via speed-increasing gear. It is also connected to the differential via a reduction gear. In EV mode, the traction motor powered by the battery propels the vehicle. The rotational speed from the traction motor is reduced through the output shaft and transmitted to the differential. The clutch is disengaged, and both the engine and generator do not operate. The traction motor delivers a maximum output of 145 kilowatts and a maximum torque of 300 Newton meters, while the battery capacity is 26.6 kilowatt hours. During deceleration, The traction motor operates as a generator to provide regenerative braking. In self-charging hybrid vehicles, regenerative braking cannot be applied once the battery is fully charged. However, in plug-in hybrids equipped with a large-capacity battery, this is much less of a concern. For more about regenerative braking in self-charging hybrids when the battery is fully charged, please watch this video. There's a link in the description. When the battery state of charge drops below a certain level, the system operates as a series hybrid. With the clutch disengaged, the engine runs to drive the generator. The traction motor operates using the electricity generated by the generator, propelling the vehicle. These graphs show torque curves for a typical gasoline engine and a typical electric motor. Gasoline engines are inefficient at low engine speeds, and efficient at mid-range engine speeds. On the other hand, electric motors are highly efficient at low speeds, but their efficiency decreases at high speeds. For this reason, during highway driving, the system operates as a parallel hybrid. The clutch is engaged, and the engine's output is transmitted to the differential. During steady speed driving, the traction motor does not operate, and the engine propels the vehicle in its high-efficiency operating range. When strong acceleration is required, such as during overtaking or on steep uphill roads, the traction motor assists the engine. There is a concern. The Sealion 6 is equipped with a 1.5-liter naturally aspirated engine that produces a maximum output of 72 kilowatts and a maximum torque of 122 Newton-meters. It is extremely underpowered for a vehicle with a curb weight of 1,940 kilograms. You can think of it as something like putting the engine from a Toyota Yaris gasoline engine model into a BMW X3. Since the Sealion 6's traction motor delivers a maximum output of 145 kilowatts and a maximum torque of 300 Newton-meters, there is no issue as long as the battery has sufficient charge. When high torque is required, the battery supplies additional power to the traction motor in series hybrid mode, supplementing the electricity generated by the engine. In parallel hybrid mode, the traction motor's output is added to the engine's output. What happens if the battery becomes so low that it can no longer supply power to the traction motor? BYD claims an EV driving range of up to 145 kilometers. Suppose that after driving 145 kilometers in EV mode, you then encounter a long, steep uphill climb. In parallel hybrid mode, the engine, which is less powerful than the one in a Toyota Yaris, has to haul a vehicle that is heavier than a BMW X3 up the hill. In series hybrid mode, the traction motor operates, but the only energy supplied to it is the energy produced by the engine. Even assuming 100% efficiency for the generator, the traction motor, and the traction inverter, the traction motor can produce no more than 72 kilowatts of output. Why did BYD's designers choose such an underpowered engine? Perhaps, the system includes a smart battery management function designed to prevent this kind of situation. Or perhaps, they judged that such a demanding situation would occur only rarely, and therefore would not pose a problem. Or perhaps, they thought that consumers should tolerate issues of this level, since lowering production costs allows the vehicle to be sold at a more affordable price. The truth is known only to BYD insiders. So all we can do is hope for a competent battery management system. Thank you for watching. If you enjoyed this video, please consider subscribing to the channel. We'll see you in the next video.